My name's Duncan Lyster, and I'm a PhD student at the University of Oxford, just going into my third year. And I just want to say a big thank you to both my supervisor, Kylie, who's here, and the other co-authors listed on this who've been hugely helpful in discussions of this work, which is, I will caveat it, is still ongoing. So I was looking at modeling the flyby of the asteroid Dinkinesh by the Lucy mission. So this was a flyby that took place in November 2023. And some work has been done on this already. So Sam Jackson's paper came out, so Jackson et al. 2025, who modeled the radiance from the primary body, Dinkinesh. And I'm really interested in seeing what we can learn by including the small satellite Selam, which you can also see in those images there in that modeling. So the Lucy mission for the uninitiated is on its way currently to the L4 Trojans. And so far, it's performed 2 flybys of main belt asteroids. And the first of these was Dinkinesh. Now, Dinkinesh was a bit of a surprise because it was thought to be a single body. And yeah, during the flyby, the satellite Selam was discovered. And actually, quite fortuitously, Selam was within the field of view of the flyby. And also within the field of view of LTES, which is the thermal emission spectrometer on the Lucy spacecraft. So that means we've got radiance data to work with. Now, unfortunately, unfortunately for this flyby, the asteroid is very small compared to the field of view of the LTES instrument at that range. So it doesn't quite fill the field of view of the instrument, and that's not really the mode that the instrument was intended to be used in. So it's designed for when it gets to the L4 Trojans, which are much larger bodies. So the idea is to get multiple fully filled field of view observations of those asteroids. So a bit more on the asteroid itself. So the main body, Dinkinesh, has quite a fast rotation period, so about 3.74 hours, and it's not tidally locked to its satellite Selam, but Selam is tidally locked to Dinkinesh, and so its orbital period is thought to be the same as its rotation period, and that's a much slower 52.7 hours. Now, that's really important because Selam is quite small. So if they had the same rotation period, you'd expect its radiance to be comparatively small compared to Dinkinesh. But because of its very slow rotation, if you assume they have the same thermal inertia, then you can find surface temperatures on Selam of as much as 25 Kelvin higher than those on Dinkinesh. And so the hypothesis going into this is that that is a signal that might be detectable in the LTES observations, despite the fact that it doesn't fill the field of view. And so with this very small lobe size of 230 meters, you can actually, look at those numbers and see that maybe the radiance is something to be investigated. So a bit more background on the Lucy thermal emission spectrometer, this LTES instrument. So this is just an example of what the data from that instrument looks like. These are from the ground-based calibration targets before launch. And so you can see 2 targets there, one at 75 Kelvin and one at 140 Kelvin. And so you can see we've got roughly the shape of a black body curve. But when you're using this instrument and you're looking at a target that has a field of view with multiple temperatures, you basically get those black body curves stacked on top of each other. So the final curve may or may not match a single temperature black body fit. So what I wanted to do was take my thermophysical model, Tempest, and take those shape models of the 2 bodies. So there's a very detailed shape model available for the main body Dinkinesh. And for the secondary body Selam, I used 2 spheres basically joined to represent that the morphology that we see there. And then simulated the flyby, so getting the field view of those 2 bodies, modeling the radiance coming off them, and seeing how that looks over the spectral range of the instrument. So nice little animation here for you to see how that works. And you can see Dinkinesh is moving around within the field of view. Now, an important caveat to this is that I haven't actually used SPICE to do this visualization. This is based on position data from the LORRI instrument, which is the visible light instrument on board Lucy. So that's definitely something to look at as an improvement going forward. So one of the first things you can do as a bit of a sanity check here to see if this is possible is to look at the integrated radiance. So the full spectral radiance, the full spectral radiance integrated for those Lucy observations. And so the graph on the left there shows you what that looks like throughout the flyby. So you can see the radiance increases to a peak at closest approach, and then it drops off again. Now, on the right-hand side is a kind of an initial run of this model to see what type of radiances we retrieve. So the blue line is the radiance from Dinkinesh, the primary body. The red line there is the radiance from the secondary Selam, and the green line is the combination of those two, so what we'd expect to receive at the instrument. And you can see the important feature there, which is there's an eclipse. And so we see this in the lorry data, that you can see that from the perspective of the spacecraft, Selam passes behind Dinkinesh. And so we'd expect that to have an impact on the integrated radiance. Now, whether you see that same shape in the peak on the left is maybe open to a little bit of interpretation, but it's a starting point to see how well we fit that curve. So this is a preliminary result of that flyby. So looking at the integrated radiance. Now, this is for a model run with a thermal inertia of 50 thermal inertia units, and you can see it's approximating the shape of that curve, which is quite nice to see, but it's certainly not capturing all of its detail. So you can see out beyond closest approach, right at the edges, I'm overestimating the radiance, and then at closest approach, I'm underestimating it. Now, this is for a smooth model result. So as I'm doing this investigation, I'm also working on the thermophysical model itself, and have just been at the very early stages of including roughness in that model. And so this is something you expect for a smooth model, because we don't get any of the shadow hiding effect, which leads to increased thermal radiance as you pass through zero phase. And the Lucy spacecraft passes through zero phase very close to the closest approach. So this is ongoing work, but I'd really like to see if I can match the shape of this peak. But I'll show you so this is basically what this curve comes from. So this is another little animation, and we're cycling through the radiance observations of the Lucy thermal emission spectrometer. So those red points are the data points for each channel. And you can see we've got a blue line, which is the modeled radiance that's come straight out of the thermal model. And then we've got a scaled radiance, which is scaled to be the same magnitude as the observed radiance. Now, we don't want to have to scale it because that shows that if we're doing that, we know that we're not reproducing the radiances. But you can see that we are roughly reproducing the right curve. Now, the scale factor between the modeled radiance and the observed radiance is quite a useful diagnostic when you're trying to get the geometry right and get the setup for those bodies right. And it's something you can also use when you're fitting thermal inertia, because that's the kind of the end goal of this, is to find an accurate determination of the thermal inertia of one or both bodies. And so if you can see that your scale factor is off in one direction, that might give you an indication of what's going wrong there. Now, as I mentioned, the smooth model underestimates the radiance. So you can see that blue curve is lower than it should be. And the scale factor there is about 1.19. Now, I have done some rough model runs, and there's quite a large parameter space to search here if you're fitting for thermal inertia and roughness. And I couldn't quite get it done in time for this. But I have got a few simple results. And so you can see this is a preliminary rough result. This is observation 3298, which is pretty much bang on closest approach within the LTES flyby series. And so you can see that it's getting a lot closer to replicating that radiance. So the next step here is to go through the full set of possible thermal inertia values and roughness values, and see what we retrieve, see what the kind of so the way that I'm fitting that is to calculate a reduced chi-square value across the full set of observations, and then seeing how close we can get that. And it's looking promising, but I'm not quite at the point where I can say with any certainty that I've constrained the thermal inertia of one or both bodies. But so to conclude, Selam's rotation being much slower than Dinkinesh's means that it does heat up more significantly, and therefore we do see that with the integrated radiance spectrum. Whether it's big enough to be observable over the noise of the instrument is something I'm still to show, but it's certainly an interesting thing to have a look at. the thing that really excites me about this is that it's possible that with observations like this, for example, at the Trojan asteroids, where we know that there are at least a few binaries that are going to be visited, there may be more than we know about, like in the case of Dinkinesh. There's this idea that maybe it's possible to show that you can't fit the data with just a simple single thermal inertia for both bodies. And that might allow us to either constrain and say that the thermal inertias are going to be both within a very similar value, or possibly that we can say that we can't fit it and they maybe will have two different values. So this is the first kind of study that I've done with the Tempest thermal model. And it's been a really interesting thing to get to grips with. And so yeah, there's a few caveats to this. One is that it is a new thermophysical model, and so there's more validation to be done on it. And yeah, the other is this is an ongoing work in progress. But yeah, the question is really, what can we do with techniques like this to constrain observations of binaries and draw conclusions about their evolution and formation? So I believe I'm pretty much out of time, but I would say I'm very lucky to have been given a second slot in this session, which will be after the next speaker, when I'll be talking a bit more about the thermal model. But yeah, if you've got any questions about this work, then please go ahead.
Thank you. Right, so questions? Oh, okay.
Toshi from Georgia Tech. Thank you so much for your presentation. This is great. I have a quick question regarding how you model the temperature, I mean the radiance. So did you consider the interaction of heat between Selam and Dinkinesh? And would that be important to consider the inconsistency of your observation?
Yeah,
And,
thank you. So
yeah.
really interesting question. At the moment, I haven't done that. So I've modeled the two bodies as on their own. So I'm not including any eclipses. Not that we know, I think that whether there are eclipses in this particular configuration. But the other thing that I'm not including is any kind of radiative transfer between the two bodies. They are quite well separated. So I think any effects are certainly going to be secondary to whether or not Selam is considered at all. But it'd be a really interesting follow-up to investigate and just see how much difference it does make to the surface temperatures. Thank you.